Hi everyone, I hope you guys are having a good day. In this video, we're going to talk about Hamiltonian paths and circuits in complete graphs. So take 3 deep breaths and let's make this math easy. So when we're looking at Hamiltonian paths and circuits in complete graphs, the stuff we learn in this video is going to help us be able to solve the traveling salesman problem that we talked about in the previous videos. So as a reminder, a complete graph is a graph where all of the vertices are adjacent to every other vertex. So these are some examples of complete graphs with varying numbers of vertices. And what we're going to look at in this video is how many Hamiltonian circuits or paths exist in a complete graph. In this complete graph, we have 4 vertices. And remember, a Hamiltonian circuit is one where every vertex is visited exactly once. And because it's a circuit, you end up back where you started. So one possible Hamiltonian circuit would be to go from vertex A to vertex D to vertex C to B and then back to A. So I'm going to write that down. Got A, D, C, B, and then back to A. Another one that I could do, I'll erase this and draw a new one, is I could go A to C to B to D and then to A. So A, C, B, D, A. Let's see, what would be another one I could do? I could go A to B to D to C to A. That would be another one. A, B, D, C, A. And I think that those would be all of the possible Hamiltonian circuits because I could also do A, B, C, D, A, but that's essentially the same circuit as the one I listed here. It's just kind of like going in the backwards order. So I think that those are all of the Hamiltonian circuits that exist in this graph. So the question asks how many Hamiltonian circuits exist, and the answer is that there are 3. And there is an easier way to figure out what all of the possible Hamiltonian circuits are without having to just kind of draw them out and figure them out. And that method is called a choice tree. So when you're creating a circuit, it doesn't really matter where you start because let's say I was looking at the circuit A, D, C, B, A. I could write it as A, D, C, B, A, or I could write it as D, C, B, AD, or it doesn't matter which vertex you start at, it's still going to be the same circuit. And so I'm just going to kind of across the board just always start at vertex A when I'm creating a circuit. So if I just consistently start at vertex A, then I have 3 different choices of where I can go from vertex A. So on my choice tree, I'm going to draw branches for each one of those choices. So I could go to vertex D, or I could go to vertex C, or I could go to vertex B. And if I go to vertex D, then I have 2 choices for where I can go from there because I can't go back to A because I haven't finished my circuit yet, but I could go to B or to C. If I went to vertex C, I could go to vertex B or D. And if I went to vertex B, I could go to C or D. So essentially, each one of these branches of the tree represent different choices that I made. So this branch right here means that I went to vertex D and then I went to vertex B. And if I go from A to D and then go to B, then the only choice that I have left after that is to go to C. And then I have to go back to A to complete my Hamiltonian circuit. And if I went to C instead of to B, then my only choice would be to go to B and then end up at A. So that would describe, let me erase this. That would be going from A to D to C, and then to B, and then to A. So that would be that one. And then I can basically do that same idea to complete all of these. So if I went to C and then B, my only choice would be to go to D and then go to A. If I went to D, then I'd have to go to B and then A. If I went to B and then C, then I'd go to D and then A. If I went to B and then D, I'd go to C and then A. And these would be all of the different choices I could make. And basically each one of these branches represents a circuit. So this top branch represents the circuit A, D, B, C, A. This one represents A, G, C, B, A. This one represents A, C, B, D, A. And A, C, D, B, A. And A, B, C, D, A. And A, B, D, C, A, like that. So all of these are circuits that start at A and are Hamiltonian circuits because I only visited each vertex exactly once. Now, if you notice, there's actually 6 circuits here, and on the last slide, we found out that there were only 3 circuits. But the reason why there's more circuits with the choice tree is because the choice tree doesn't distinguish between circuits that go forwards and backwards. So for example, this circuit, ABCDA, so ABCDA like that, that's the same circuit as this one, which was ADCBA. And so these 2 circuits are the same circuit, just one of them goes around like clockwise or one direction and one of them goes the other direction. And similarly, this circuit here is the same as this one, and this circuit is the same as this one. They're just going in different directions. So the number of unique Hamiltonian circuits is 3, because the choice tree basically double counts those circuits because it counts it going one direction and then going the other direction, but it's still the same circuit. So we can use the same strategy to find the number of Hamiltonian circuits in a complete graph with 5 vertices. So I could say, okay, well, let's say I start at vertex A again. Well, from vertex A, I have 4 different choices of where I could go. I could go to B, or to C, or to D, or to E. And then if I choose B, then I have 3 choices of where I could go, which would be C, D, or E. And all of these ones would also have 3 choices. And I'm not going to write the whole tree out just because that's a lot of writing. But you can imagine that there would be 3 choices branching off of each one of these original branches. And then once you, have gone to vertex C, then you could choose to go to vertex D or E. If you chose to go to D, then you'd have to go to E before going back to A. This would look like D and then A. And you'd have a similar pattern for all of the rest of the branches of the trees, where you'd have 2 branches and then you'd only have 1 choice of where you could go after that. So ultimately, the question we're asking is how many Hamiltonian circuits are in this graph. We're not necessarily asked to list them all because that would be a really long list. And so if we only want to know the number of Hamiltonian circuits, we don't have to actually fill the whole choice tree out. We just need to know how many branches are in the choice tree. So if you want to, you can fill the whole choice tree out, and say like, okay, well, like this branch right here means that I have the Hamiltonian circuit A, B, C, D, E, A, and you could go through and fill that out for all of these. Or you could kind of think about, well, like how many branches will there be? Like if I were to fill out this entire choice tree, how many branches would there be? And the way you figure this out is you look at how many choices there are at each level. So at this first level of branches, we had 4 choices because you start at vertex A and you have 4 choices of where you can go. You choose one of those vertices, and after you go there, then you only have 3 choices of where you can go after that. So the next level of branches each has 3 choices that branch off of that. And then after you visit your third vertex, then you only have 2 choices of where you can go after that. And then at the 4th level of your choice, then you can only go to 1 vertex. So like we'll use a specific example. Like if you chose to go to vertex B, then you could go to C, D, or E. But if you choose to go to C, then you only have 2 options. If you choose to go to D, then you have to go to E on that last choice. And then you also only have 1 choice for where you can go to end up back at the beginning where you started. And so when you look at all of these choices at each level, notice that the number of branches in the tree multiplies with each level. So if we go back to this example where we actually wrote out the entire tree, notice that there were 3 choices for the first level of choice, 2 choices for the second level, and then 1 choice and 1 choice. And so if you notice, the total number of circuits that we end up with our tree is 6, which is the same thing as 3 times 2 times 1 times 1, because like each one of these 3 choices branched off into 2 more choices. And so that gave us 6 branches. And then these 1 choices didn't actually create any new branches. They just kind of like extended them. And so if we wanted to figure out the number of Hamiltonian circuits in this complete graph, we would do that by just doing 4 times 3 times 2 times 1 times 1. And this is a super useful method of using choice trees to help you count the number of possible things without having to list them all out. And we'll use these some more later in the semester in the probability unit. But for right now, we just need to know that this choice tree would give us 4 times 3 is 12, times 2 is 24, times 1 would be 24. So this choice tree is going to give us 24 different Hamiltonian circuits. However, remember that the choice trees don't distinguish between going forwards around the circuit or going backwards. And so the number of unique circuits that we would have is actually 12, because all of the circuits are going to be double counted. Like it will be counted once going one direction, and then the choice tree will count it again going the opposite direction. And it's still the same circuit, whether you're going around the circuit in one direction or if you're going backwards. And so you would take this number and divide by 2, because the choice tree will double count the number of circuits. And so the number of Hamiltonian circuits in a complete graph on 5 vertices would be 12. And that would be the number of Hamiltonian circuits there. And you can use the same strategy even if you have a really big complete graph. So in this complete graph, it looks like we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Looks like we have 12 vertices. So I could go through the same process and I could say, okay, well, if I start at vertex A, I have 11 choices of where I could go. So if I wanted to draw a choice tree for it, I would basically have like 11 branches, which would be a very huge choice tree to draw. So I'm not going to draw it, but you can imagine there would be like 11 branches of all of the different choices of where you could go from vertex A. So you would have 11 choices, and then after you choose one of the vertices to go to, the number of things that would branch off of that vertex would be 10 choices, because you can't go back to vertex A yet, and so you have 10 other options of where you can go. And so that would create 10 times more branches. And then after you go to that second vertex, then you have 9 choices of where you can go. And essentially you're going to keep on doing this until you've visited all of the vertices. So you'd say, okay, I start at A, then I go to the second vertex, the third vertex, the fourth one, the fifth one, the sixth one, there's 7 choices for the 6th one. And then the 7th one, the 8th one, the 9th one, the 10th one, and then the 12th one is your last vertex that you haven't visited. So there's only one choice for where you can go. And once you're at that last vertex, then you want to close up your Hamiltonian circuit. So you would just go back to vertex A, which is just a single choice. And so to figure out the number of Hamiltonian circuits, you would figure out what 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 is. And when you calculate that out, the number that you actually get is 39916,800, which is 39,916,800. So the number of Hamiltonian circuits in this complete graph that are unique is like huge. It's like almost 40 million. And so this number gets even bigger and bigger and bigger depending on how many vertices you have. So like if you had, 20 vertices or something like that, that would be an even bigger number. So the way that we calculate the number of Hamiltonian circuits in a complete graph with n vertices is calculated with this formula. So you may not have seen a factorial before. So the symbol for a factorial is an exclamation mark. And essentially what a factorial means is like if you did 4 factorial, this would be 4 times 3 times 2 times 1. Or if you did 7 factorial, that would equal 7 times 6 times 5 times 4 times 3 times 2 times 1. So a factorial basically means you like multiply a number by decreasing numbers all the way down to 1. And so the reason why it's n minus 1 factorial, if you have n vertices, is because if we go back to this slide where we were finding the number of circuits in 4 vertices, notice that we didn't start with a 4, we started with a 3. And the reason we started with a 3 was because we started at vertex A, and then we had 3 choices of where we went from vertex A. So there's 4 vertices, but one of the vertices was the one that we said was our starting point. And so like we didn't have to make a choice for that. Like we just said, okay, A is where we're going to start the circuit, because it actually doesn't matter in a circuit where you start. So I'm just going to start at vertex A. And then from vertex A, we had 3 choices of where we went from there. And so that's why the formula has n minus 1. So like if you were trying to find the number of Hamiltonian circuits in a complete graph on 25 vertices, you would do 24 times 23 times 22 times, go all the way down to 1. So that's the factorial piece, is basically counting the number of branches in your choice tree. And then the dividing by 2 part is because your choice tree will double count your circuits, because it will count it going one direction and then it will also count it going backwards. And so once you figure out how many branches are in your choice tree, which is the n minus 1 factorial, you want to divide by 2 because you don't want to double count the same circuit twice by counting it forwards and then counting it backwards. So that's the number of Hamiltonian circuits in a complete graph on n vertices. And the number of Hamiltonian paths is a little bit different because if we look at this graph, there's only one Hamiltonian circuit, and it's basically the entire graph because that's the circuit that visits all the vertices once. But if you are looking for Hamiltonian paths, that's going to be a little bit more, because if we look at it, there's this path, so I'll write it out, A, B, C. There's also this path, BCA, and then there's also this path, CAB. And so the number of paths is more than the number of circuits, because with a Hamiltonian path, it does matter which vertex you start on, because with a Hamiltonian path versus a Hamiltonian circuit, if you start on a different vertex, it changes the result. Like with a circuit, it doesn't matter whether you start at A, B, or C, because you end up back where you start. Like It just kind of like creates this circle that you could go around an infinite number of times. And that's different than a circuit because in this graph there was only one Hamiltonian circuit, but with Hamiltonian paths, it makes a difference depending on which vertex you start on. And so like if we think about this in terms of a choice tree, when you're finding Hamiltonian paths, the first vertex you start with does matter. Like you can't just always start at A. You have to account for all of the different vertices you could start at because they're not all the same. So there's 3 Hamiltonian paths while there was only one Hamiltonian circuit. And the reason for that is because with Hamiltonian paths, it does make a difference if you start at different vertices. Because with paths, you're not going back to where you started, versus with circuits, you are, and it kind of creates this cycle or this circuit where it doesn't really matter where you start on it, you're still going to create the same circuit. So the choice tree for Hamiltonian paths looks a little bit different because you have to choose where you start. So in this case, you would choose, okay, I'm going to have A be my starting point, or I'm going to have B be my starting point, or I'm going to have C. And then once you choose A as your starting point, then you could go to B, or you could go to C. And then once you've chosen B, you have to go to C. Or if you choose C, you have to go to B. And same thing here, you could go to A or C. So that's what the choice tree would look for that part. And you'd have A and B. So this is what the choice tree would look like for a Hamiltonian path. And also notice that I didn't go back to where I started at the end, because with a Hamiltonian path, you only visit each vertex exactly once, and you don't go back to where you started. So when you look at this, again, though, notice that the number of paths we determine just by like drawing them is 3, but the choice tree gives us 6 options. And that's because this branch of the choice tree, which represents the path ABC, is double counted right here because this one is CBA, which is the same path. It's just whether you go forwards or backwards on the path. And so when we do this choice tree and we calculate it as 3 times 2 times 1, because you have 3 choices for where you start, 2 choices for where you go from there, and then 1 choice for your last vertex, that's going to give you 6. But the number of Hamiltonian paths is 3 because you're going to divide by 2 to account for the fact that your paths were double counted for forwards and backwards. So if we apply this to a complete graph on 4 vertices, you could go through and draw them all out, or you could do a choice tree and you could say, okay, well, with paths, it matters where you start. So I have 4 choices for where I could start. I could either start at A, B, C, or D. So I have 4 choices for that. And then I have 3 choices of where I can go from there. So if I choose A as my starting point, then I could go to B or C or D. So I'm going to multiply by 3 because each one of these 4 choices is going to branch off into 3 more. And then from there, then I have 2 choices of where I could go. And then after that, I'll only have 1 choice. And that will create my Hamiltonian paths. And each one of these is going to branch off into 2 choices and then 1 choice. So I can write this as 4 times 3 times 2 times 1. And that's the number of branches in my choice tree. So I'd have 4 times 3 is 12, times 2 is 24. However, remember that I am double counting the paths because the choice trees will always count them in both directions, but it's still the same path whether you follow it one direction or the other. And so I would take this number and divide by 2 to find the total number of Hamiltonian paths in this complete graph. So in this complete graph, there would be 12 Hamiltonian paths. So the formula for the number of Hamiltonian paths is very similar to the formula for the circuits. The only difference is that you don't have the n minus 1, you just have n factorial. And the reasoning for that is because if you're finding a path, you have to choose out of all of the vertices which one is your starting point. And then with each choice, you just subtract 1, and that is the factorial part. But with circuits, it doesn't matter where you start on the circuit, whether you start on vertex A or vertex B, because it's a circuit and it just kind of goes in a loop over and over and over again. And so with circuits, it doesn't matter where you start, but with paths, it does. And both of them are divided by 2 because the choice trees will count the paths and circuits forwards as well as backwards. So why don't you guys go ahead and try this? Use this method that we talked about to find the number of Hamiltonian circuits in this graph, as well as the number of Hamiltonian paths. So why don't you guys pause the video and try this example on your own, and then restart the video to see how I solved it. All right, so on this one we have 1, 2, 3, 4, 5, 6, 7 vertices. So if you want to, you can just plug the numbers directly into the formula, or you can think about what the formula means. So you can say, okay, well with a circuit, with circuits it doesn't matter where I start. So I'm just going to say I'm going to start at vertex A, and from vertex A, I have 6 different choices of where I can go from there. So I'm going to start off with a choice tree that has 6 branches going off of it. Then from each of those 6 branches, whatever vertex I decide to go to, I have 5 choices of where I can go after that. Then after that, I have 4 choices, 3 choices, 2 choices, and then at the very end, I only have 1 choice of where I can go to have my path go to the last vertex. So if I do 6 times 5 times 4 times 3 times 2 times 1, that equals 720. So there's 720 branches in my choice tree. But remember that the choice tree double counts the circuits, going one way and then the other. And so I want to divide this entire thing by 2. And 720 divided by 2 is 360. And so there's 360 Hamiltonian circuits in this graph. And you could also calculate this with the formula, because the formula for Hamiltonian circuits is n minus 1 factorial over 2. And in this case, since there were 7 vertices, you would do 7 minus 1, which is 6 factorial divided by 2. And that's basically what we calculated out here. So you can use the formula if you like. I think it's helpful to think about what it actually means because it helps you understand it more. So that's how you would figure out the number of Hamiltonian circuits. And then for Hamiltonian paths, it would be very similar, except for the fact that you have to choose where you start. And then after you choose your first vertex, then you have 6 choices of where you can go from there. And then for your next vertex, you have 5 choices because you can't go back to your starting one or the one you already went to. And so you have 5 choices, and then you have 4 and 3 and 2, and then finally you just have your last vertex as your choice. So if you multiply all of those numbers together, that gives you 5,040. But again, remember that the choice trees will double count the paths going forwards and going backwards. So we're going to divide by 2 to make it so we're not double counting that. And if I do 5,040 divided by 2, that gives 2,520. So there would be 2,520 Hamiltonian paths. So that's how you can calculate the number of Hamiltonian paths and circuits. And this is really important for when you use the brute force method. So we'll talk about that in another video. But this is a key concept you need to understand in order to be able to do the brute force method. So if you have any questions, let me know, and I hope you guys have a great day.